Let's talk about the estimation problem. Imagine that you want to go to the moon and you need to measure your position and velocity in space, but in space you don't have a global positioning system to guide you. You can only approximately know your relative position with respect to your previous position using a model. In addition, you can also use sensors to measure your position. However, this measurement will not be perfect because every sensor is subject to noisy conditions. Then, what is the best way to know your position and velocity? Here is where the Kalman filter comes into play, as it fuses information from the model and the noisy measurements to provide an optimal position and velocity estimation. The Kalman filter was introduced by Rudolf E. Kalman in 1960 in a seminal work entitled A New Approach to Linear Filtering and Prediction Problems. The Kalman filter has the ability to cope with uncertainties in both system and measurements. An extended version, known as the Extended Kalman filter, was developed by NASA Ames staff. Its most renowned application was in the navigation computer used in the Apollo program. Since then, NASA has been using it in many of its navigation systems as a critical part of the missions. To understand how the extended Kalman filter works, let's go back to our trip to the moon, where the spacecraft can be modeled by nonlinear dynamics represented by a differential equation with uncertainty. The sensor measurements are corrupted by uncharacterized noise. This sensor noise is assumed as a normal Gaussian distribution, described by its covariance matrix of unknown value R, which is critical for the optimal performance of the extended Kalman filter. Let's analyze the extended Kalman filter. It consists of two stages, the prediction and the update. The aim is to estimate the states of a dynamical system, such as the position, velocity, and acceleration in our spacecraft, where the only available data are the noisy measurements. The filter's local optimality, in the sense of minimizing the estimation error variance, relies on the proper choice of the covariance matrices characterizing the Gaussian distribution. Hence, a long-standing problem in the implementation of optimal Kalman filters is the accuracy in setting the value of the covariance matrix for the noise in the system's output. The importance of the Kalman filter lies in its wide range of applications. For instance, combat systems based on air and missile defense and navigation systems are aided by Kalman filters. Kalman filters are the cornerstone of sensor fusion, where data from multiple sensors are merged to reduce the amount of uncertainty that may be involved in autonomous navigation problems. In the industry, the filter is used to estimate systems variables instead of installing expensive sensors and dealing with inaccuracies and precision errors. This class of industrial applications has been called sensorless due to the eliminated need for more sensors since the states of the systems can be estimated. Kalman filtering is also used by international environmental monitoring initiatives, such as Argos, that uses satellite telemetry to collect meteorological and oceanographic data around the world for scientific and environmental applications. A restriction in the application of the extended Kalman filter is that it assumes that the noise is described as a Gaussian normal distribution characterized by the covariance matrix R. But this assumption is a problem in itself, since in the real world, noise is not always Gaussian. In practice, this implies that the estimation made by the extended Kalman filter will not be the best. There are several approaches to find the best value for the covariance matrix R, where its definite positiveness is required to guarantee the filter stability. However, noise characterization is still an open problem. The Analytic Behaviors Control Systems Lab presents The Evolved Extended Kalman Filter by Leonardo Herrera, María del Carmen Rodríguez Niñán, Eddie Clemente, Marlene Mesa Sánchez, and Luis Monay Arredondo. Given the relevance of the problem, we propose the Evolved Extended Kalman Filter, which is a new version of the Extended Kalman Filter where genetic programming is applied to develop nonlinear functions that replace the unknown covariance matrix R of the noisy measurements. The Kalman criterion is used to guide the GP in the construction of the fittest replacement functions. Parameters of the filter and the only available noisy measurements of the system are used as terminals for the GP. This guarantees its straightforward application. The Evolved Extended Kalman Filter has been tested in a logistic map system. This example was chosen due to its importance in many research fields, such as cryptography, modeling of population growth, economic models, and synchronization, to mention a few examples. The richness of this nonlinear system can be seen in its bifurcation map, where its dynamics range from stable equilibrium points, oscillations, and chaos. all of them with variations of a single parameter alpha. Then, why is our entry the best? Reason 1. Active patents show investments in the development of functions and procedures for an accurate estimation of the covariance matrix R to ensure optimal performance of the filter. This open problem has a large global market. For example, in 2020, the autonomous cars market size in the US was $1.45 billion. The aerospace and defense industries in the US amounted to $874 billion in total revenue in 2020, and the global market for industrial robotics is expected to grow to $214 billion by 2030. Thus, the Evolve Extended Kalman Filter has the potential of being patented. In addition, our method can produce a large set of patents, one for each of the nonlinear functions obtained for a particular system. Reason 2. The Evolve Extended Kalman Filter has been tested in a logistic map system. The GP was set to perform the search with a fixed value of alpha equal to 3.7. The validation stage considers the introduction of variations from 3.5 to 4, that is, where the richness of the system dynamics is high. In addition, the constructed functions maintain a great performance regardless of the introduction of variations in the initial conditions of the filter and system, and the increment of the noise amplitudes in the measurements. Reason 3. The main feature of the GP is its ability to construct definite positive solutions that guarantee the internal stability of the filter, making the Evolved Extended Kalman Filter theoretically feasible. Many of these solutions are synthesized, and they can be straightforwardly implemented in practical applications. This is because they only use intrinsic variables from the filter and the noisy system's measurements. Reason 4. Great performance is preserved regardless of the introduced variations. The Evolved Extended Kalman Filter outperforms the original Extended Kalman Filter, since the Evolved Extended Kalman Filter is trained to minimize the estimation error variance regardless of having non-perfect white Gaussian noise. Reason 5. By introducing the Kalman theory as a guide for the GP search, the computational load is reduced. A small population in the order of the hundreds is enough to find optimal replacement functions in a few generations, 100 in this case. In addition, for the logistic map, a small dataset of noisy measurements is used for the evolutionary process. These settings are small compared with the traditional settings of GP implementations. In summary, we believe that this proposal fulfills the following criteria. The fulfillment of criterion A is based on the novelty of the method and the patentability of the set of nonlinear functions for a particular system. This is supported by the found active patents where lookup tables, quadratic functions, optimization techniques searching for constant values of the covariance matrix, and the use of default estimated constant values for this matrix are considered. For criterion D, a large set of replacement functions created with GP has the theoretical property of being positive definite, which makes them feasible, regardless that they were artificially created. In addition, they have demonstrated robustness against variations in the system, the filter, and the noise in comparison with the original human design. For criterion E, the Evolved Extended Kalman Filter has outperformed the original Extended Kalman Filter. This can be explained by the Kalman theory assumption that the noise affecting the measurements is zero mean Gaussian, when in practice and even in simulation this is not perfectly guaranteed. In contrast with the traditional Extended Kalman Filter, the GP builds suitable solutions using the non-perfect noise and considering only intrinsic variables from the filter and the system's noisy measurements. Thus, its implementation is straightforward and does not require further adjustments. Finally, criterion G is fulfilled since this problem dates from the conception of the Kalman filter. The optimality of the filter is based on the proper choice of the unknown covariance matrices of a zero-mean distribution to model uncertainty and noise. However, in practice, noise is not necessarily either Gaussian noise or even Gaussian with a constant covariance matrix. Thank you for considering our work.